All right, here we're back again for part segment or section 3.2. We've got instantaneous velocity and speed. Instantaneous velocity is, as it sounds, it's the velocity at any given instant. That is, at any given one short moment in time, as opposed to average velocity, which is the average over a period of time. The instantaneous velocity is defined more scientifically as the velocity at any given moment or point, and it's often referred to just as velocity because that's the more commonly used concept anyway. If we mean average velocity, then we will normally say average velocity, but if we say just velocity, then we normally mean instantaneous velocity. You can think of it as being the average velocity between 2 points that are infinitely close together. So 2 points separated by essentially zero distance. That would be the instantaneous velocity. So for example, if we define x as being a function of t, so when we write x with t in parentheses after it, that's basically what we mean is x is a function of t. And it is, if you think about it, if something is moving, then its position in space, which is what x represents, is a function of time, because its position, if something is moving, its position in space is changing over time. So therefore, its position is a function of time. So that's what we mean. The average velocity between 2 points would just be the position at time 2 minus the position at time 1 over time 2 minus time 1. That is the change in position over the change in time. And you can think of time 1 as just being some time, the original time, and time 2 would be time 1 plus the change in time between time 1 and time 2. And I'm introducing this idea because the formal mathematical definition for average velocity is average velocity, which is a function of time, is the limit as the time interval approaches zero of the position at time t plus delta t, or in other words, time 2, minus the position at time t, or in other words, time 1, divided by delta t, the change in time, which is t2 minus t1. Or in other words, the derivative of x as a function of t with respect to time. And this didn't come out so well, so I could just write that again as this. Oops, close the print. So that's what that means. Derivative of x as a function of time with respect to time. So what we're talking about here is the limit of average velocity as delta t approaches zero, or in other words, as the 2 points you're taking the average velocity between come closer and closer together. And essentially, there's practically nothing separating them. Or you can think of it as the derivative of x with respect to t. Another way of doing it, and a way of illustrating the mathematical concept, is to find the slope of the tangent line to the position versus time curve at the moment of interest. And there's a diagram on page 111 that's drawn a little bit better than I can reproduce it here, so you might want to look at that. Anyway, what I've got here is if you've got a curve of position versus time, and it goes like this. So basically, the item is traveling in one direction, and then it turns around and comes back in the other direction over time. And at the point where it changes directions, the velocity would actually be zero. And it looks like right about here at the peak of the curve, that's where it changes directions. So when you have a curve of position versus time, anytime you have a peak or a trough, say if this curve started heading up again like that, The same would be true for the minimum. Maxima and minima correspond to changes in direction. Also, you can look at the average velocity between 2 points, because basically the slope of a position versus time graph will be in units of position over time, or in other words, meters per second. So the derivative or the slope of a graph of position versus time, the slope will be the velocity. And if you want the average velocity between, say, time 1 and time 2, then you just take time 1, where time 1 falls on the position versus time graph, and the point where time 2 falls on the position versus time graph, and you draw a line through those 2 points. And if you want the average velocity between those 2 points, all you have to do is find the slope of this line. And the slope is just delta y over delta x, or in other words, you take the x and y coordinates of the 2 points, and it'll be the y coordinate for point 2 minus the y coordinate for point 1 over the x coordinate for point 2 minus the x coordinate for point 1. That'll give you the slope. And that will be the average velocity between those 2 points. You can do the same for any 2 other points, and say you could do it for time 3 to time 4, and you can find the average velocity between time 3 and time 4 by, again, finding where time 3 falls on the data line for position versus time, and where time 4 falls on the data line for position versus time. Draw a line between those 2 points and find the slope of that. And that will give you the average velocity between time 3 and time 4. Notice that time 3 and time 4 are closer together than time 1 and time 2 were. You can go to another extreme and take 2 points that are basically right on top of each other and plot those 2 points on the curve and find the tangent line. Essentially, tangent line is the line between 2 points that are right next to each other. So that theoretically, anyway, the tangent line only contacts the curve at 1 point. And if you take the slope of the tangent line, that should give you the velocity at t5. So in other words, the tangent line, or if you take the slope of the tangent line, what you're getting in this instance is the slope of the line that basically it's the slope of the line between time 5 and another time that's infinitely close to time 5. Or in other words, you're getting the instantaneous velocity at time 5. So the average velocity between time 5 and delta t, which we're taking as being infinitely small, where delta t approaches 0 is what that means. Or in other words, that's the instantaneous velocity at t5. So this is how you can do it graphically. If you know what point you're interested in, just very carefully draw the tangent line to the curve at that point and find its slope, and you'll have the instantaneous velocity. Or in other words, the derivative of the xt curve, that is position versus time curve, is equivalent to its slope at any given moment. You could find the instantaneous velocity at any point on this curve. If you wanted to know what the instantaneous velocity was at t1, then you just get out a ruler and, to the best of your ability, you draw a tangent line at t1, and it would look something like that, and you find the slope, and that would be the instantaneous velocity at t1. So instantaneous velocity, as with any kind of velocity, is a vector. The SI units would be meters per second. And any point where the instantaneous velocity is 0 would be a maximum point or a minimum point. So instantaneous velocity should be 0 at the peak, and it should be 0 again at the trough. And in practical terms, what a peak or a trough means in a position versus time curve is that the item or the object is changing directions. Okay, so it was going in a positive direction for a while, but then it turned around and went in a negative direction. So it changed directions. The point at which it changes directions is going to have a zero velocity because it was going at a certain velocity in the positive direction. Then it's going a certain velocity in the negative direction, but between positive and negative comes zero. So the velocity would be zero whenever the item is changing directions. We can look at finding velocities from a position versus time graph in example 3.2. And we have something that looks like this, and we want to find the velocities for each segment. Okay. There, that's a little better. So I've divided the segments up into A, B, and C. We've got the positions from the origin in meters, 0.1, 0.2, 0.3, 0.4, 0.5, and 0.6, and times in, say, 1 second to 2 seconds total with divisions in between. And if we want to find the velocity for segment A, that's going to be the change in location, or delta x, for segment A over the time interval for segment A. Okay, so that's going to be the final position for segment A minus the initial position for segment A. Final position for segment A is 0.5 meters. And the initial position for segment A was 0 meters. So that's 0.5 minus 0, or 0.5 meters. The time interval is, again, the final time for segment A minus the initial time for segment A. The final time for segment A is 0.5 seconds. The initial time was 0 seconds. So that's also 0.5, but it's seconds because it's time. And so the velocity would be delta x over delta t, which is 0.5 over 0.5, which would be 1 meter per second. So that's the velocity for segment A. For segment B, the change in location for B would be the final position for segment B minus the initial position for segment B. For segment B, this is segment B right here. The final position for segment B would be 0.5 meters. The initial position for segment B would also be 0.5 meters. So that's 0 meters for the change in position. The time interval for segment B would be the final time for segment B minus the initial time for segment B. Final time for segment B was 1 second. The initial time for segment B was 0.5 seconds. My drawing's a little off there, but you get the idea. So that's 0.5 seconds for the time interval. So the velocity is going to be 0 meters over 0.5 seconds, or 0 meters per second. Notice, again, that when the slope is 0 for a line in the position versus time graph, that means the velocity is 0. And it's going straight across, which means the slope is 0. The change in location for segment C, change in location would be the final location for segment C minus the initial location for segment C. Final location for segment C was back at 0 meters. The initial location for segment C was at 0.5 meters. So that's 0 minus 0.5 because it's final minus initial. And that's negative 0.5 for the displacement. The time interval would be the final time for segment C minus the initial time for segment C, which is 2 seconds minus 1 second, or 1 second. So the velocity would be delta x over delta t, or -5 meters over 1 second, or -5 meters per second. Okay, and if we want to know average velocity over all 3 segments, would be the change in location would be x final minus x initial. At this time, it would be for the entire thing. So the very final x position would be 0 meters. And the initial position was 0 meters. So that's 0 meters for the change in position. The change in time over this period would be the final position, which was 2 seconds, minus the initial position for the entire thing, which was 0 seconds. And that's 2 seconds. The velocity is just delta x over delta t. Delta x is 0 meters. Delta t is 2 seconds. For an overall velocity for the entire process of 0 meters per second. And that's because you ended up back where you started. So the displacement is 0, and therefore the velocity is 0. Okay. Speed, on the other hand, would be different. If you're looking for total distance traveled, it would be 0.5 meters for segment A, plus 0 for segment B, plus 0.5 meters again for segment C. So that's 1 meter total distance traveled. And the time would be 2 seconds total for the entire process. So 1 meter divided by 2 seconds would be 0.5 meters per second for speed, the average speed, which does not take account of the direction. Okay, so here we talk about speed, as long as I was on the topic of speed. That brings us to speed. The speed is just the distance covered over a given time period without regard to direction. Its speed is a scalar, so it has magnitude but no direction, and therefore it's always positive. Okay. The average speed over a given time period would be denoted as S for speed with a line over it. And that's the total distance traveled, distance, not displacement, over the time elapsed during the travel. It's important to remember, though, that unlike a lot of other scalar quantities versus vector quantities, speed is not necessarily just the magnitude of the velocity. And that's because distance is often not the magnitude of displacement, because displacement is the net distance traveled. Again, if you end up back where you started out, displacement will be 0, but the distance will not be 0. Just like in that previous example here. Displacement for the overall process was 0, but the distance for the overall process was 1 meter. So, the absolute value of 0 is 0, but the distance was 1, not 0. So we have to keep that in mind. Speed is not necessarily just the magnitude of velocity. And as I mentioned before, speed is always positive because it's a scalar and it doesn't consider direction. And the instantaneous speed, though, is the magnitude of instantaneous velocity. So speed instantaneous is the absolute magnitude of v as a function of t, which is the instantaneous velocity. There is a table of typical speeds on page 114, which you can look at. It's kind of interesting to compare, typical speeds of various activities, but you can do that at your leisure. I'm not going to take time here to go over it. Calculating instantaneous velocity. And as I mentioned before, one way to calculate instantaneous velocity is to draw a tangent line to the curve of position versus time at the moment of interest. And if you do it carefully, you can find the slope of that tangent line, and that will be the instantaneous velocity at the moment of interest. Alternatively, and usually more accurately, you can use the derivative of x versus t. And that becomes easier if you have some kind of standard form for the equations. The typical form for position versus time would be something like this. Oh, sorry. For position versus time, it would be something like this over here. X as a function of time equals a, which is some constant number, times t raised to some power, which we'll call n. And if that's the case, then taking the derivative is actually pretty easy, because when you take the derivative of something like this, what you do is to take the derivative, the power of the variable is multiplied by the coefficient, and the new power of the variable is 1 less than the previous power. So in other words, if the function of position versus time is constant a versus t raised to the n power, then the derivative would be n times constant a times t raised to the n minus 1 power. N would typically be some number, so you would just take the number n times the number a and write down whatever that is for na. And then it would be t raised to whatever the original power of n was minus 1. Okay, so that's your derivative. And so if something is given in this form, it should be pretty easy to deal with. And we're going to do some examples like that next, but I think we're close enough to the end of this segment that I can end it here, and we'll pick this up in the next segment.